G'day, in this video we're going to be looking at the second half of our electric field calculations. So again, we're looking at dot points 4.1, 0.3 and 4, and in this video we'll be looking to cover the equations that we did not look at in the first part. So our key learning intentions today is to first compare both the work done as well as the change in potential energy for objects that may be either in a gravitational field or an electric field. We'll then look to quantitatively define voltage, and generally today we're looking at building our capacity to apply potential energy and work concepts to charged particles when they're placed in electric fields. So first up in this video, I wanted to look at work and potential energy, which is present when analysing objects placed in either gravitational or electric fields. We covered gravitational fields earlier in this Year 11 course, and what I wanted to do is draw parallels between what we already know about gravitational fields to some of these concepts that we're learning today about electric fields. First thing to consider, which is really important, is this statement up here, that W, which is work, is equal to negative delta U. In other words, work is equal to negative change in potential energy. This statement is correct when we reflect on the law of conservation of energy. Essentially, as potential energy is lost, it's being converted into some form of kinetic energy, which is doing work. A conclusion that we can make here is that work is a result of potential energy transforming into kinetic energy, upholding the law of conservation of energy. And we can relate work to other measurable values by using the equation W equals Fs. In other words, work is equal to the force on an object over a set displacement that the object travels because of that force and the work being done. In this diagram here, we can see that there are actually a lot of similarities between a gravitational field and an electric field. Both gravitational and electric fields apply forces to objects, which result in velocities that are parallel. However, the key difference here is gravitational force is dictated by the mass of the object, and forces caused by electric fields are due to the charge of the object. To compare both of these fields, what I'm going to do is use the work equation to show that we can create work equations specifically for objects in gravitational fields and a work equation specifically for objects which are in electric fields. First off, let's look at gravitational fields. This is actually going to be a recap of concepts from Module 1 and 2. An equation we should be really familiar with is Newton's second law, that F equals ma. And specifically, we also talked about the idea that when looking at forces caused by gravitational fields, that we could rewrite this equation as F is equal to mg, where g is the acceleration due to gravity. Applying this equation F equals mg to our general work equation at the top, I can substitute mg in for F, meaning that the work done can also be written as mgs. In other words, the mass of the object times the acceleration due to gravity times its displacement. In practice, we used a slightly different version of this equation, and it was that delta U is equal to mg delta H. Now, these two equations are quite similar. Here, we're looking, instead of work, at the change in potential energy. In other words, as we lift or drop an object, we'll either be gaining potential energy as we raise it or losing it as we drop it. And that's going to be dependent on the mass of the object, g, the acceleration due to gravity, and the change in height. Effectively, both versions of the equation, though, do describe the same concept. On the other hand, when we look at electric fields, our force equation looks slightly different. And this is an equation that we used in the previous video, and that is that F is equal to QE. In other words, the force applied on an object is equal to its charge multiplied by the strength of the electric field. Similarly to what I did for the gravitational field, we can rewrite our work equation by substituting in QE into F, giving us work is equal to QE. However, in your data sheet, you will see this equation as work is equal to EQD, where D is being used for displacement instead of S. Slightly annoying considering that we've defined displacement as S previously. It should be something that's pretty easy to remember as we go. Now, when comparing our two equations that we have on the bottom, we should be able to see that there are very key similarities. First off, delta U and W represent the energy of moving particles. Either we're talking about the change in potential energy that the particle or object has, or in the case of work, we're talking about how much work that object has done as it's moved. And the other terms on the other side have pairings as well. The first one that we're going to look at is M and Q. The mass of an object or the charge of a particle in an electric field are both particle properties. We also have another pair of variables, G and E, which both describe properties of the field. And finally, delta H and D describe displacements of objects. The key point that I'm trying to get across when doing this comparison is that fields, no matter what type of field they are, can behave in quite similar ways. Generally, they make objects or particles do some form of work. In other words, convert potential energy to some form of kinetic energy. And the amount of work which is done is dependent on three key factors. The property of the particle or object itself, which actually interacts with the field, the size or strength of the field itself, and then the amount of displacement which the object experiences when in the field itself. Just to tie everything together a little bit further, I do want to look at relating this EQD equation to a couple of different versions of energy variables. So we know that work is equal to EQD, but similarly we could say that this work is equal to negative delta U, which is the negative of the change in potential energy. In other words, if delta U was negative, we were losing potential energy. That would result in work being positive, that work was being done, which also means that this work would be equal to a change in kinetic energy as well, because the work that is being done is resulting in a charged particle gaining kinetic energy. As we can see, this W equals EQD equation can be found in your data sheet. However, in your data sheet, there are a few other key equations which are related to concepts like work and charge, but include this variable here, V. We may recognize V from year 9 and 10 science, that being voltage. Generally speaking, when we're looking at voltage in stage 5 in years 9 and 10, we're primarily focused on voltage in an electric circuit. We don't go into full depth about what voltage actually is or how it works. That's what we're going to look at now. And to do that, we need to unpack these two concepts, electric potential and potential difference. I'm going to look at electric potential first. So electric potential is essentially the measurement of electric potential energy per coulomb at a specific location in an electric field. So if I were to have an electric field and I were to place a charged particle in that field, this measurement of electric potential would tell me how much potential energy that charged particle would have per coulomb of charge that the charged particle actually has. To sort of reword that concept, I'm going to make a comparison between two charged particles, a green particle and a red particle. We'll say that the green particle has 1 coulomb worth of charge, and the red particle has 2 coulombs worth of charge. Essentially, in this scenario, assuming that the electric potential was uniform around the field, and both particles were stationary, we would assume that the red particle would have twice the amount of electrical potential energy stored inside the particle because it has twice the charge of the green particle. This is defined by our equation here in our data sheet that V is equal to delta U on Q. V here is our electrical potential. Delta U is our electrical potential energy. And obviously Q here is our charge. Technically, though, electric potential is a measurement of the electrical potential energy that the particles actually have, not delta U, which is the change in electrical potential energy that a particle may experience. So electric potential V should actually be U on Q. When we start introducing our changes in or our deltas, this is where we talk about potential difference, because delta in our equations represents a change in or a difference in. And that's our potential difference here. So potential difference measures the change in electrical potential energy per coulomb between 2 points in an electric field. So potential difference technically is actually delta V. Change in electrical potential is delta U. And again, because we're working per coulomb, this is our per charge or our per Q. Meaning that for potential difference, delta V is equal to delta U on Q. Note that both equations that I've written in both of these slides don't exactly match up with the equation that's in the data sheet. The data sheet doesn't really give us a way to discriminate between electric potential and potential difference. It's something that I would keep in mind, but generally speaking, if you are applying this equation, you should still find it fairly easy and straightforward to substitute the appropriate variables into the appropriate place. If you're working with a potential difference, it's going to be some sort of voltage, which is measured in V, or you may see units of measurement which are in joules per coulomb, and that's just got to do with the fact that we've got potential energy divided by charge as our way of calculating for potential difference or voltage. It is a little bit messy, but as you start completing some of these practice questions, these intricacies and complexities shouldn't be too much of an issue. So an example of where there may be a potential difference is on the positive and negative terminals of a battery. So when there is a potential difference between 2 points in an electric field, such as on the ends of the battery when you actually make the circuit, that's what's actually going to cause particles to move and generate a flow of current. In other words, we lose some of that potential energy, that delta U, which moves our charged particles, our electrons, which we know have a charge of QE, or 1.602 times 10 to the negative 19 coulombs. In this last slide, I just want to have a look at one or two more of the equations which are in the data sheet and show you that once we have the other equations that we talked about already, we can begin to relate also the electric field strength and the potential difference which may exist. So today in this video, we've already been exposed to two key equations. That is, work is equal to QED, and that delta U is equal to delta VQ. I've just done a little bit of a rearrangement there. And we also acknowledged that work was equal to negative delta U, or negative the change in potential energy. Knowing all of that, we can actually combine both of those equations. So because we know that EQD is equal to negative delta U and that delta U is equal to delta VQ, all I've done is I've just changed this equation to be negative delta U is equal to negative delta VQ and combined the non-negative delta U expressions together, resulting in them turning into a new equation. From here, I'm just going to rearrange the equation so that it reflects this equation up here, that E is equal to V on D. So note in this proof that while what I've written is slightly different to what is in your data sheet, again, there are a few discrepancies between what's in the data sheet and their consistent use of delta to demonstrate potential difference, not electric potential. And as well, there is a negative symbol that has slipped its way into the equation as well. There are some reasons for this, and even though the equations that we're looking at today all contain three variables and they're really quite simple to solve, one of the tricky bits about applying these equations is going to be making sure that we're understanding the concept behind the problems that we're being presented to us, and as well are able to communicate our answer using the correct polarity. And these polarity discrepancies with our use of positive and negative terms is something that we're going to be unpacking in class when we start to undertake some of these practice problems. Now, the last thing for this video that I also want to show you is how we get this equation here, that work is equal to QV. So this equation relates the work done by a particle to the potential difference in an electric field. And really, it's just a variation of the equation below, that W is equal to QED. And again, here I'm going to demonstrate that we can combine other equations that we've already derived and already know about to be able to produce other equations which relate other variables. So here I'm looking at the concept that V is equal to ED, just a rearrangement of this equation, and that W is equal to QED. Here we can see that there is an ED in both equations, and that V is just equal to VD. So I'm going to take V and insert it where this ED part is in the other equation. And in doing so, I've been able to write an equation which relates the work done by a charged particle when placed in a particular electric field with a set potential difference. Now, considering how many variables there have been in these electric field calculations, I thought I'd also include a bit of a variable summary, which identifies all the potential variables that we're working with, their associated symbols, and potential units of measurement that you may see or need to report with. Thank you very much, everyone. We're not going to do too many calculations in this video. I just wanted to be able to try and keep this video quite short, but still introduce a lot of the concepts that we're going to be using in our coming lessons. We'll practice a bunch of calculations using these formula in class. The next video that we're going to be looking at is going to be focused on equipotentials and will be the last concept that we cover, which is focused on electrostatics and charge. Until then, have a good one.